Hello and welcome to this low-level JavaScript series on building a fantasy game console. In this slightly different format of video, today we're going to start building a game using the assembly language. And the game that we're going to build is going to be something like Frogger. If you haven't heard of Frogger before, it was a game in which you play as a frog and you are attempting to cross a landscape full of obstacles. Such as cars or rivers, although I don't really understand why rivers were an obstacle for a frog, but in the game they certainly were. And we're going to build a sort of, or we're going to begin building a sort of slimmed down version of that. Okay, so the basic idea is that, let's say this is the frog. The idea is we want to get the frog across the board to the end goal. And along the way, there are going to be, for instance, cars that are crossing the road from one side to the other, which we're going to have to avoid. And if we don't avoid them, that's going to be game over. If we manage to make it past the cars, then there's going to be a river, and along the river are going to be floating these logs. And as the logs move past, the frog has to jump onto the log, and then the frog and the log, they'll move together on a trajectory, and as they pass, we'll try to get still moving together, still get the frog to jump to the other log, and of course to the end. And this is going to bring us into various places and various different ideas about the architecture of the fantasy console and writing games in assembly and the approach to that. We're going to see some of the difficult spots and some of the ways that you can approach these kinds of problems. The frog, the cars, the logs, these are all going to be sprites. And if you don't know what I'm talking about at all, then it might be worth taking a look at the previous two videos, the first of which explains the architecture of the machine, and the second wires everything up together. Okay, so the frog, the cars, the logs, the end goal probably are all going to be sprites. Sprites have various attributes such as an XY position and a drawing order and a tile that represents them and a sort of animation offset which can be applied so that you can play animations based on different tile setups in memory. But we will have to write quite a bit of logic ourselves, for instance, collision detection and that kind of thing. And basically, let's just dive in and get started. The code, as I left off, is pretty much the same. I added a little bit of debugging functionality to the CPU just to make it a little bit easier to diagnose problems, inevitable problems that come up while writing assembly. It's very easy to introduce bugs because you basically have to run a virtual machine in your mind as you build the game, but we'll see this as we go through. Okay, so the first thing is the setup is pretty much the same. The only thing I've done is I've added a tile to tile memory, which is sort of just a black ring around the outside. I can show you in the code as well. Not particularly exciting. So just a set of raw bytes to represent this tile. F is black in the palette. So these are the colors of the palette. F is black, and 0 is actually transparent, although it looks black here. So basically, what we have is a ring of black, and that allows us to just have a grid on the screen, which is very high contrast and very easy to see where the tiles are, and we can count tiles and should make things easier. And we have two sprites that we set up in memory. They're not doing anything. Nothing responds to any movement. The code at the moment is just purely an infinite loop. So the first thing we're going to want to do is we're going to want to put something that represents the frog on screen. And we'll just do solid colored tiles for now, and we'll tidy that up later. So we'll put a green tile down here somewhere, and we'll have it just respond to input. That's the first thing to do. So it's going to be a bit messy to write code in here. So one of the things I want to do is I want to add a file. We'll just call it frogger.js. And in here we will export a function. And the function is going to take in some properties from mostly just addresses of things, because I don't want to move everything out of the other file into here, but we can inject some things. And what we're going to return is just a string of assembly code, which we can feed to the assembler. This is it. This is pretty much the setup. So let's just go back into here. This is the code we had from last time, so let's just cut that out and put it in. And that's the arguments. Okay, so here is the assembly code. And so we'll want to call this function, we'll just call it frogger. And we'll pass in some arguments to this as well, or some values. And let's import that in the top. Frogger. So now we have a frogger function. Everything should be still working. And yeah, we need to set up some sprites. So we'll set up a sprite. So we have 2 sprites here already. Let's get rid of one. And let's make some addresses for ourselves here. So I'm just going to put the frog, like the frog's address. It's actually just going to be equal to the sprite table offset. This will be the first sprite. Although we might want to move that, because at the moment this means that the frog will be drawn under every other sprite, which is fine for instance, the cars, because the frog is getting under the car, but it will be worth drawing it on top of the logs. So we might actually want to put, for instance, the logs in the first positions, and then the frog, and then the cars. We'll see as we get to that. Okay, so then let's change these offsets to be the frog. And you'll remember from the previous episode that these 3 offsets, this is for the X position. So the X position is in the sprite table, we have a 16-byte data structure that represents a sprite. And the first 2 bytes are for the X position, the next 2 bytes are for the Y position. Then there is a byte which represents its tile. So that's the 3 things we have here. It would be nice to make constants for this, and in the assembly language, we even have a construct called a structure, in which you can describe semantically the layout of a given structure, and you can interpret a memory address as a structure, and so you can talk about it more semantically. We may do that as we begin cleaning the code up, but in the beginning I'm just going to get things set up correctly. So this is the frog's X position. Let's put the frog somewhere down here. So that's like halfway across. We have 30 tiles across. So let's say we want to put him on the 15th tile. That would be 15, or rather it would be 14 times 8, because this is 0 indexed. And each tile takes up 8 pixels up and down. So this would put it roughly in the middle. So now we have this pink square in the middle. And we want to put it right down here on the bottom. So we have 14 tiles in the Y direction. So that means we want to have 13 times 8, and that puts us down at the bottom. So that's perfect. The frog should be green. We have 3 shades of green in the current palette to play with. B looks like a nice shade, nice dark shade. We could also have a lighter frog, more of a lime green. Let's go with B for now. So let's put, let's use OXB, and now we've got a nice green frog. Okay. So now what we want to do is we want to respond to input. Input is taken in from the keyboard, and every frame, the values of whether you've pressed any of these buttons on the keyboard, or the gamepad, or whatever you want to call it. This could actually be a gamepad. We've got up, down, left, right. We've got some kind of main interaction buttons, A and B, and we have start and select. And these are mapped to the arrow keys, to A and S, which are next to each other on the keyboard, and to space and enter for start and select. So we're going to look at these arrows, and each key is stored as a byte in memory, and the byte is either value of 0 or a value of 1. It's not a particularly efficient storage mechanism, considering we have 8 buttons and we could store all of those in a byte. But in this assembly language, we don't have any single instructions right now to deal with addressing bits. And because of that, that would make it a little bit cumbersome to look at, so in a fast way, to look at the values in these memory locations. So instead, every button has its own byte. So we're going to want to look at this place in memory, which is here, 2620. So let's pass this input offset into the Frogger assembly code so we can use it in the code. So we're also going to want to pass the address of the frog. And I'm going to rename that to lowercase input, so we just have some clean looking constants inside. I think that's all we should need for now. We're going to generate the code from this function. So let's save that, save this, and let's bring in our frog and input lines. Okay, so the structure as we had before was that we would start and there's no code. We just jump immediately into this wait label, and all that does is move the address of this wait label into the instruction pointer, causing an infinite loop. And then at the end of every frame, an interrupt is fired. We've called that the after frame interrupt, or the after frame. And we've provided this address to the virtual machine as the interrupt handler, and all we do in there is we return from the interrupt. We're not doing anything, but we may want to, or we will have to actually perform some checks to make sure we ran all the code of the game. We won't be able to run all the code of the game when the game is finished. Probably won't be able to run it all in a single frame. That's normal. If you have so many things to do and so many collision detections and things like that, and this virtual machine does not run at a very fast clock rate as compared to its frame rate. So the frames are drawn much faster than the machine can run instructions. So in this case, we would expect that most of the game code won't get run before a frame is drawn. It shouldn't have any large effect, as long as we may get some graphical glitches if we're halfway through setting up how drawing should be done, and then a frame is drawn, and then in the next frame we finish sort of what we should have done in a single frame. So we may see some sort of not tearing, but sort of sprites moving one after another instead of in sync. But those are problems we'll see and deal with as we get closer, and there are some optimization solutions that I have in mind for being able to run more instructions per frame. Okay, so first things first, we're kind of like this wait. I'm just going to rename it to end of game logic. And sort of, if we're getting to this point, it's going to signify that we sort of ran all of our code and we're done. And we'll set some values up in there. But for now, the first thing to do is going to be checking the input. So let's check if the up button was pressed first. And yeah, we'll spell check correctly as well. It's not necessary as it's a label, but let's do it anyway. Okay, so what we're going to do is we're going to move the value of the up button into the registers, and we're going to check it against something. And if up is pressed, we're going to manipulate the frog sprite position. That's it. So we're going to want to move, and actually I added specifically for the fantasy console, I added some 8-bit instructions. So we actually have a move 8 instruction. And what that says is instead of loading a 16-bit value from memory, which is the typical word size of this machine, we can load specifically an 8-bit value. It's not necessary, but again, it's one of those things that if we didn't have this instruction, we would have to load a 16-bit value and we would have to mask off the 8 bits we care about. And if those 8 bits happen to be the upper half of a word, we would have to then shift those 8 bits down. And this just becomes a little bit cumbersome to perform, so it's just better to have 8-bit reads and writes. Writes especially are more annoying because then you have to read the value more than once and all things together so that you get them in the correct way and then write them back to memory. We don't have to do that because we have 8-bit instructions. So what we're going to do is we're going to move the value of an address. So we need to use the address of operator, or this signifies that we're talking about something in memory. And we have the address, that's the input address. So we're going to use like interpolated JavaScript values here to do that. Instead of constants in the assembly language, which we could use. And just to make things a little bit easier, I'm going to add some functions for this. So let's say we're trying to load from an address. We're going to have a numbered address that we're going to pass to this. That's going to just return us a string that starts with this address operator, and then we'll put this number. And we have to specify numbers in hexadecimal. So let's just make a hexadecimal function as well. And all we're going to do with a hexadecimal is to do n.toString, give it 16 to say that we want to interpret this as a 16-bit or a base 16 value. And we will pad the start of that number up to 4 characters wide with zeros. And that will just make sure that we always get 4-digit hex numbers in the code output, which is just a little bit easier when debugging. So this is going to be our final function. So the address just does the address operator and converts our number to hexadecimal. So let's do this. The address, and the address is just input. And up is the first byte in the input table. So it's literally just this address. But if we were looking it down, it would be this address plus 1. And we can calculate those in line here because we're doing it in line in JavaScript instead. So we're going to move this value into the accumulator register because the accumulator is where comparisons happen, branching comparisons. So what we want to do is we want to jump to sort of the next check if this is 0. If we haven't pressed the button, then we're going to sort of try and check the next thing. So what I'm going to do is I'm going to set up a couple more labels here. So we're going to have check down press, check left, and check right. Down, left, and right. And we're going to want to jump if the value in the accumulator is not equal to 0. And to specify 0, we would do like a literal, this is the symbol for a literal value, and we would do something like this, or just this. I'm going to actually add another function for this, because this is an easy place to make bugs, and the parser is not very forgiving in its error messages at the moment. This is a nice, simple way of avoiding those kinds of errors. So it's just going to be the same thing again. Except this time we're talking about a literal value or an immediate value, and it's just going to be a literal 0. And the place we're going to jump to is the value of this label. And to get the value of that label, we can use this syntax, which is basically tells the assembler, like, hey, use, we can actually do calculations inside these, but this exclamation mark followed by the name of a label or another symbol tells the assembler, hey, look at the corresponding value of this symbol. And the corresponding value of the symbol will be the address that this represents. Okay, so essentially, if this was 0, we would jump down here. So that means that if we write more code onto this label, this is only going to run when it's a 1. So we know we've pressed this. So now we can actually manipulate the value, in this case, the y value of the frog. So at the moment, the frog is down here, and it has a high valued position because 0, 0 is up here, and the largest values are down here. So, sometimes in graphs, 0, 0 is down here. On the canvas, and I haven't changed the coordinate system to be different, so on the canvas, the 0 position is up here on the top left. So that means that the y value is now high, and to move upwards, we need to subtract from the y value something. The amount that we're going to jump, imagining the frog is jumping, the amount that we're going to jump is, let's say, half a tile. And what I would like to do is make this into an animation so that lasts some time. So if you press the up button, you sort of do half a jump, or you sort of do a double jump. You do hop, hop. But it's only represented by one button press. So I want to do half a tile and then the other half. But that takes some time. But for now, we'll just make it so that one press corresponds to half a tile of movement. So what we actually need to do then is we need to get the current value of the y position. So we do that in basically the same way as we've done this. Except it's a 16-bit value, so we don't use move 8, we use move. And we want to do the address, but this time the address is going to be of the frog. Now, we don't need to offset this because, we do need to offset this because we're looking at the x position, we need to look at the y position, so we need to offset by 2 bytes. And we want to move that into some register. And the register we want to move into doesn't really matter. Let's just move into R1. Now we want to add a literal value to R1. So let's add a literal value of 4. But actually, that's not true. We need to move, let's just write R1 there so it's complete. We actually need to move -4, -4, because we want to subtract. And there is actually a subtraction instruction, but I would rather use the add and then use 2's complement to actually sort of do a addition of a negative number. And I have a video on 2's complement, so you can check that out. And there are plenty of other resources to see how 2's complement works. But basically, if you have a fixed number of bits, so in this case 16 bits, then you can sort of create the negative version of a number by inverting all of the bits and adding 1. So let's create a function called 2's, which is really a 2's complement negative number, which takes in an n, which in this case will be something like 4, which is going to be a negative. Actually, let's call it negative instead. So we're going to take in a negative n, and we're assuming to give back a literal here, so I'm just going to call the literal function. But we can do the bit manipulation here. So we'll take n, and we'll do tilde n, which is flip all the bits. We're flipping the bits of a JavaScript number here. JavaScript numbers are 32 bits. And we don't want to flip all of the bits that were zeros in the higher parts to ones. So we're going to AND this whole thing with FFFF to ensure that the number that we're dealing with is only ever going to be 16 bits wide. And then we can add 1 to it. And that's it. That's how we'll get our 2's complement negative. And if we add this to a number, it will basically, what will happen is we'll end up overflowing and we'll come back to the right point. And if you check out the video that I have on 2's complement, you can see how 2's complement is kind of like a big circle. And when you add numbers, you end up running around the circle by the correct amount to actually do subtraction. That's how it works. It's worth watching if you haven't seen it. Okay, so we're going to add -4 to R1, which is going to move us up, and then we need to write that back into memory. And the way we would do that is we're going to move the the value which is in R1, we're going to move that to the address, which is the frog plus 2. So we know how to do addresses now. Frog plus 2. Okay, so we can check that this works, but first we need to sort of address what's going on here, because what's going to happen is even if we press the button, we would have to press it on the very first frame that the machine ran, or otherwise we just end up back in this infinite loop. So what we're going to do is we're going to, here at the bottom, we're going to add a variable, basically. We're going to add a place in memory where we're going to store some information. We can do that with this data8 directive, and I'm going to call it end of logic. Let's call it has ended, and let's use camel case instead to sort of signify that it's not a label, a sort of address label, but it's a piece of data. And I'm just going to set this to literal 0. And so this is going to be 1 byte at a particular memory address, which we can refer to with this name. And it's going to start out at 0. So basically we haven't reached the end at this point. And what we're going to do is, let's make a second label here. End of game logic loop. So in the first part, we'll first we'll move an 8-bit value, and it will be the literal value of 1, and we're going to move that to the address, which is has ended. So basically, at this point, we're signifying that we have ended, and then when we come to the end of our frame, we're going to want to sort of jump back to the beginning. This is kind of assuming, well, perhaps actually for now it's simpler to not do any of this, to not do this and actually just to jump back to the start. The problem with doing that is that it's sort of, you'll get a kind of unpredictable feeling frame rate, which if we do things this way, it will kind of, the frame relation to the game logic is a little bit more coupled together. And if it's not, then it's going to run as fast as possible. And perhaps, you know, if certain pathways in the code are not taken, then we'll end up skipping large parts of the code and we'll run the game logic faster. So the frog might end up feeling like it moves faster in certain situations, which is probably not ideal. So no, let's do things this way. So when we reach the end of the frame, we need to check this value. So we need to say, let's move this value somewhere into memory, into one of the registers. And this kind of gets also to a sticky point of when you do interrupts, and the way that interrupts now work means that the registers aren't stored, which means that if you use the registers in your interrupt handler, then you're going to basically overwrite something. So there needs to be a sort of unsafe register, at least one unsafe register. And for now, I'm just going to conventionally say that R8 is an unsafe register. So if you write to R8, then you've got to expect that could at any moment sort of change on you. So we're going to move this 8-bit value, which is at the address, and we're not going to use the functions because I'm going to use the reference to this has ended label. So we're going to move the value that's at this address, and we need to use, well, this would be a literal otherwise, so we need to express that this is an address. We want to take the value at that address and we want to move it into R8. Now there is a problem here, and that is that we need to store, we're going to need to overwrite the accumulator register, but we can restore it. So at the beginning we can just push the accumulator register onto the stack, and at some point in the end we will pop that off because we need to keep the stack in the right, we need to match the number of pushes and pops, otherwise we could actually run out of memory by sort of blowing our stack up. So we're going to save the accumulator on the stack, and we can move its value into the accumulator, because that's where comparisons happen. So, and we're going to make a second label here. I'm going to really uncreatively call this after frame 2. And this is basically going to be like, we're now going to check, like, did we get to the end of the game logic? If we didn't get to the end of the game logic, we actually just want to jump back to wherever we were and continue running the code. So we don't want to go to start, we want to go back wherever we were. That's the typical behavior of return from interrupt. On the stack is the address we came from, and return from interrupt will take that address off the stack and just jump back to it. So in this case, we're going to check in the same way as this jump here. So we're going to check, hey, if this is equal to 0, or if this is not equal to 0. Wait, I feel like I maybe made a mistake here as well. If the value in the accumulator is not 0, we jump into it. So this is wrong. We actually should jump if it is equal to 0. And it's the same thing here. We should jump if this one is equal to 0. So we didn't reach the end of the frame, and where we want to go is after frame 2. Okay, so let's write for this case first. So we didn't reach the end of the frame. Okay, so what we can do is we can pop back into the accumulator because we pushed the value at the beginning. Now we need to pop, and then we're just going to return from the interrupt. That's it. Okay, and in the other case, well, we know that we did reach the end. So what we want to do is we need to actually, now let's pop the value in that was the accumulator's value. Let's put that in R8 for a second. We can blow R8 up. And then what we're going to do is we're going to pop we could just pop into the accumulator. So we can restore the accumulator, and then we can pop into R8, because this is fine. We'll just keep whatever was in the accumulator. Then we're going to pop what's in R8. Now this second pop is the instruction pointer. That's where we were going to jump back to. But now we're going to jump back to start instead. So what we're just going to do is we're going to push the address of start. And we don't need to use the address of, because this is just the value in the label, and the value in the label here is always the address. So now we've overwritten that sort of return, the return location. So now we can RTI. And you can see that we've destroyed what was ever in R8, but that's convention. So, oh, one more thing. We also need to write 0 back into this this thing, so that when we come to the end, we know that, yeah, we can restore this back to 0. So we're going to move a literal value of 0. So lit 0. We're going to move that to the address, which has ended. So move 8. So now we're moving the 0 back. We're popping the accumulator, and I think that should work correctly. But I wouldn't hold my breath. It looks like I have made a mistake because we're not drawing to the screen. Okay, so we got a pass error. So I made a mistake in the assembly somewhere. Let's take a look. So jump equal. I wonder if the jump instruction actually does require these to be address pointers. I think it might be. So these just need to be marked as addresses. Now we've got to debug a pause. Expected end of input. So move 8. Oh, okay, this also doesn't have an address of operator. No, that is correct. So we're reading from this address. And here we're actually moving. Okay, so let's move that just to the side here, close the debugger, and we press up, and the frog does not move. So mistake has been made. So now we need to debug this. Let's have a think. So I wonder if here we move this literal value to has ended, and we're jumping in this loop. Push the value in the accumulator, move this value it has ended into the accumulator, and check if it's equal to 0. And if it is equal to 0, we're jumping to after frame 2. We know for a fact, given that we're only running about 5 instructions up here, that it's going to be a 1 for sure, or it should be a 1. Let's confirm that. Let's put a hardware breakpoint. This is one of the debugging instructions that I've added. This basically, if you have the debugger open in the browser or in Node, this will create a debug statement, which makes it possible to see what the value of all the registers are. So here we hit the debugger. It's just, we're in the very first callback. And now, because we're in the context of the CPU here, we can check out the value in the register. So let's get the value in a register. And the value we want to check out. No, let's get the value of... Yes, do we have... I've added a little bit of... I thought I'd added some code to dump out all the symbols here as well, so we could see the address of... so we could see the address that we put this data. But essentially, okay, we can just work it out, because this address represents this instruction. This is a 2-byte instruction, and then return from interrupt is a 1-byte instruction. So if we take this address and we add 3 to it, should get the value of this, and then we can read that from memory. So this.memory.read get uint8, and it's going to be from this address, and it's a 1 as expected. Okay, so what I'm going to do is I'm going to put a breakpoint here now, so in after frame 2. So then we'll just make sure that this isn't some fluke, that it actually, we can confirm that it is working in that way. Break, so we hit the breakpoint, and probably don't have any kind of frame count. I don't know if no, we don't have anything that counts frames. So we can't double check that it is the first frame, but well, it should be the first frame. Okay, so then in this interrupt handler, we're then going to move a literal 0 back. We're going to pop the accumulator. Then we're popping the old. So I guess actually a simple way of looking at this would be just to put a breakpoint here at start. And then if this is going wrong, like if we're getting stuck back in this infinite loop, what should happen is we'll break one time and then we'll never break again. So let's confirm that assumption. So here we've hit the first breakpoint, and now we're hitting more breakpoints. And now we're just caught in this loop. So, okay, so we are So that's not the problem. So the problem is perhaps just in the input reading code. So we're reading an 8-bit value from the input address, and we should be looking at the up arrow. That is the zeroth part of this. So we're reading that into the accumulator. Then we're jumping. If it's equal to 0, then we're going to jump down here, which is basically end of game logic. And otherwise, we're going to move. Well, let's put a breakpoint here. And then we can make sure that like this will only happen if we press up. And did we hit a breakpoint here? Is this actually paused? It is. So the problem here, of course, is the add instruction. The results of add always go to the accumulator. So we're moving back just the position that was already there. It's of course not going to work. No breakpoint. Let's refresh. All right. And what we're seeing here is that it's going half a tile, then the other half, and the renderer never clears the canvas, apparently. Even though we did write that into the renderer, it just doesn't happen. So at the beginning of a draw callback, if we've made it through, I'm just going to say r.clear. All right, great, input. This should be fairly straightforward to copy and paste now. Seems I've frozen, but that shouldn't make too much of a difference. All right, so in this case, for down is offset by 1. So down is the second byte here. And if it's not equal, then we're going to want to jump to this next one, which is checking left. We still want to move the Y position into R1, but instead of adding a -4, we just want to add a literal 4. So we want to go the other way around. So we've copy and pasted that code. Move up, move down. So up and down, now working. Great. And left and right should be pretty straightforward as well. I'm actually going to copy from this one because moving left also involves negative numbers. So here we're checking input plus 3, which is left. We're going to check if that's 0, move to right. And here we need to just load the X position, which is just at the address of frog. And we're going to add -4 to that, and we're going to move that back to just the address of frog. So up and down, working. Left is not working. Oh, apparently I'm reading right first, so that's interesting. So up, down, oh, okay, no, I added the wrong offset here. So 0, 1, and I went to 3 instead. Okay, and then for right, we can copy this. We'll want to, here we'll want to do 3. And here we're going to jump to, I'm just going to make a new label, which is going to represent check input end. And then this will allow us just to like move the sections of code around, without worrying about the exact order. We can sort of move this whole thing as a chunk of code. So when we're done, we'll jump to this end, and we'll want to add a literal, and we're writing into the X. So I believe that should all, so we've got up and down, left and right. Okay, so movement taken care of nicely. And even though it seems like we can move by 2 positions in the same frame, we actually this is happening over 2 frames. So this is the frame rate if I hold this down. Okay, so next then. All right. So now we're going to have some cars, for instance, as we saw in the very bad diagram. And we'll put the cars somewhere on the first few rows. We have quite a few more rows than are shown here, so let's give the frog a little bit of space to move around properly. And this is going to be somewhere where we update the cars. Alright, so we're going to need to put at least 1 car in. So this is how we can set up so the cars start at frog plus 16. So it's happening at the next address over from the frogs, and we'll put all the cars in one line or contiguously in memory. It's actually the first car. So let's make the cars orange. Let's use 7. And we want to start the car at 0. Well, let's start one of them 0, so going from left to right. And not on the last row, but let's say 2 rows up from the player. And if we check that out, we've got a car here. So we can move, a little bit up without flattening ourselves while we're just learning to move around. And we want to move this car from left to right at a given speed. So we have 16 bytes in the sprite data structure, but we actually have 9 bytes as part of the second half of the structure, which are just sort of free to use. So let's use 2 of those bytes to represent a speed. Now we're not going to need 2 bytes actually to represent speed, but it will just be a little bit easier for all the arithmetic if it works on the word size. Now the first 7 bytes are used as the for the actual machine values of the fantasy console. So from byte 8, a 0 indexed 8 onwards, we can actually use those for free. So let's set a uint 16, and it's going to be at cars plus. We could set it at 8, but let's set it at 9, just for alignment purposes, even though we have no alignment sort of critical things in this, and there are no costs at reading different alignments in the fantasy console. We'll put this on the 9th byte, and we're going from left to right, so we can just have a speed value, and I'm going to make it that it moves by 2 pixels per frame. So it's moving a little bit slower than the frog jumps, but at continuous velocity. Alright, let's pass in the address of cars into the frog, and then we can reference it here. And so when we update the cars, we can already write this code in a little bit more of a generic way. So let's even put multiple cars on screen so that it's not just completely devoid of meaning here. So let's add 16 to this, and then with the same offsets. Instead of starting at 0, let's start this other one on the other side of the screen. So we'll start over here on the next row up. So this is the 29th index here. So if we do 29 times 8, so now they're on the same row. Let's move that up one. So on the 10th row. Okay, so now we have two cars, and we're going to say that this car actually moves right to left. And so here we've got a speed value, but we need this again to be a 2's complement value because we want to add. We just want to keep the code all the same. We want to use add everywhere, regardless of whether it's a positive or negative number. So let's just do what we know about 2's complement, which is invert the number 2, mask off all the bits that aren't relevant to the machine, and add 1. So we've got now a 2's complement speed for this, and we have 2 cars. Although maybe we'll have more. So let's down here load another piece of data. We'll call it n cars, or actually I'm going to call it cars offset, and it's going to start at 0. And the thing that we're going to do here is we're going to sort of loop around in this basically in this little routine until we have iterated over all the cars, and we'll use this value in memory to address that. So so in order to check that, we need to first, well, we're going to need to do quite a bit of manipulation here. So I'm actually going to add another function up here, and I'm going to call it comment, because the assembly language doesn't have any comment facilities right now. And it'll be quite a simple, like essentially no op, but it will just allow us to write comments in line. And I'm going to do that just so that I don't make any mistakes here, because I'm fairly certain that with the number of operations and with the movements that happen between registers, that it's quite likely that I can make a mistake. So to avoid that, I will write some comments. So the first comment can actually use tag syntax just to make it a bit clearer. I don't know if that makes it clearer, but okay. So no, it probably doesn't actually. What we're going to do in the first place is we're going to load the cars offset. So load cars offset into the accumulator. So we do that by move 8. The value at cars index offset. We're going to want to move that into the accumulator. And now we're going to consider this to be done if this is equal to hex 20. And the reason we do hex 20 and not hex 2 is because the sprite structure is 16 bits, and we can just add 16 bits every time, and it costs no less than adding 1, so it's a simpler mechanism to keep track of the addresses. So let's do that. I'm going to add another label here called end of update cars. And let's add a jump. Jump if equal, and we want to check the literal value. Literal value hex 20. If it's equal to hex 20, then we're done here, and we can jump to the address represented by end of update cars. Okay. Now, the comments make easier to read here. I'm not sure. Now, if we get beyond this point, then we know that we're still in the loop. So now what we want to do is we want to actually use this offset that we have to sort of get the address of the actual car that we're dealing with. So we can do that by we know the address of where cars start, so we just need to add this offset. So let's we already have the offset in the accumulator, so what we can do is we can add the literal value of cars to what we have in the accumulator. Now we'll end up in the accumulator. So let's make a comment here that's just place address of the current car into the accumulator. Okay, so we've done that. Now we need to just do all the typical stuff. We want to just move this car left to right, right to left, whatever. And to do that, we need to just do what we did for the frog, which is just move its X position into a register, add its speed value, which is just at another part of its structure, and then write it back to its value. So we're going to load the X position into, doesn't really matter, let's say R1. And we need to preserve what we have here. We need to preserve this address of the car because we're going to need the accumulator to do the arithmetic. So let's maybe first, before we do that, place the base, place the car address into R5. I don't know, for no good reason other than it's not one of the main registers used for computation. So it's just sort of a storage place for now. So we can do that with just move the accumulator to R5. It doesn't actually move the value of the accumulator, it just copies it. So load the X position into R1. Well, that's simple. We want to move the value using a pointer or using the address, which is stored in a register. So we're going to use the value stored in the accumulator register. We want to move that to the accumulator. So now the accumulator, or we're going to load it into R1. Yeah, so let's load it into R1. So now the R1 actually contains the X value. Now we need to move the speed value into a different register. So in order to calculate that, we need to take that value that's in R5, calculate the value of the speed. What would you call this property? The speed property of the car. The address of the speed property of the car. So in order to do that, we need to add R5, which contains the base address of the car. We need to add 9 to it because 9 is where we placed this this speed property for both of these. So we can do literal 9, add that to R5, which places that address in the accumulator. Place in the accumulator. Okay, so now, and now what we want to do is we want to get the actual value of that. So put the value of the speed property in the accumulator. So this is sort of the same thing as here, but we will move the accumulator this time. So we're moving whatever is at the address currently in the accumulator to the accumulator. And finally, we can calculate the new speed. So calculate new speed, place in accumulator. So in order to do that, we need to add the accumulator, which contains the speed offset, and the current X position, which is in R1. So now the new speed is in R1. Then we're going to move that back into the position for X of the car itself, which is just the address which is in R5. So move the new X value to the car's X. So the way we can do that is move the value which is in the accumulator to the address which is in R5. If all went well here, if all went well, then we just updated the car's position. And now we need to, let's bring this down a little bit because it's getting a tiny bit cramped. It's like all that logic goes together. We've got nice comments to illustrate it. Now we need to update the index. So do we still have the index anywhere? The index was in the accumulator. Maybe it would be best to update the index before doing anything else, just because we have it in the accumulator right there. We're also using the, yeah, so let's move the value in the accumulator to R5, just to copy it there for a moment. We'll increment, so we'll add a literal OX10, which is 16, to the accumulator. So now that's the new index, and then let's write that back here. So we're doing the inverse of this operation. So move what's in the accumulator to the car offset as an 8-bit value. And then we'll move whatever was in R5 into the accumulator. So now this is just like writing this back. Write the next index into memory. The next car offset into memory. Okay. At the end of update cars, we're going to need to set that back to 0. So let's do that before anything else. Let's move literal 0 into the address, which is represented by cars offset. Cars offset. And I feel like, yeah, that's done correctly. Yeah, okay. So at this point, we've reset the cars index. And we've updated all the cars, and the only thing we need to do at this point is to jump to the top of the car update loop, which we can just do by writing the update cars address into the instruction pointer. And let's see what error I've made. Wrote a lot of assembly there. So here I made a mistake, and it's at the move 8 value. So move the value of the accumulator to this address. Ah, okay. I know what this is. When moving a value, moving an 8-bit value from a register to an address, we have to specify whether it's the low part or the high part of the register. So in this case, it's the low part of the register. So we don't actually use move 8 because that's ambiguous. How do you know if you're talking about the lower half or the upper half? So there are 2 different instructions for that. I have some ideas about creating like a slightly different assembler parser setup, such that we can get a little bit better error messages out of this to hint at what you might have done wrong. Sort of creating a parser that doesn't pass what you think it does, but just gives you a good error for what you probably meant. Okay, that's good. I don't see any cars. That probably means that we just ran them off the edge. So let's reset. And that looks to me like the 2 cars are updating correctly. That's great. There's no collision or boundary control here, but that is, I'm pretty happy with that. So you can imagine here that we're trying to jump. If the car can go over, yeah, that's a pretty good step. So what we'll do in the next episode, because this is already quite long, if I take a look, what we'll do in the next episode is check the bounds of these cars and perhaps introduce some collision detection. But for now, thanks for watching, and I'll see you next time.